Coffee.
Coffee.
Yeah.
Thank you, Stelios. Yes, great pleasure to have the opportunity to talk to you. What I'd like to talk about is some work that we've been doing, I guess, over the last 10 years, really, trying to develop techniques for synthesizing materials with more control than you typically would have in a conventional flask-based reactor. And we've focused most of our efforts on electronic materials where we're interested in optimizing physical properties. So, for example, we're interested in optimizing the molecular weight distribution of polymers, or maybe we're interested in optimizing the spectral characteristics of quantum dots or chromophores. And these are classic examples where in order to get control over the property you're interested in, you ultimately need a lot of control over the manner in which you carry out the reaction. So our solution to this challenge is to work with microreactors. So the general idea is we carry out the reaction in thin tubes or channels, and we flow reagents through those channels, and within the channels we can carry out all the standard chemical processing steps. So you can heat, you can cool, you can mix, you can separate, you can filter. Pretty much any process that you can carry out in a conventional flask can be adapted to work in flow. But the advantage of moving to a flow environment is it frequently gives you more control over the manner in which the reaction is carried out. So, for example, you can mix more quickly, or you can dissipate heat generated in the course of a reaction in order to make sure that the reaction takes place at a fixed temperature. In addition, by shrinking down the size scale on which we perform a reaction, we can get much more uniform reaction environment, both in terms of the chemical composition of the reaction mixture and in terms of the thermal distribution through the system. So microreactors come in various forms, and you can see two examples here. These two pictures here show chip-based systems. So these are glass or plastic substrates into which channels are etched. So you etch channels in one substrate, take a second substrate, place it on top to form a lid, and you flow the reagents through. And this is really how we started out in the area of flow chemistry, working with chip-based systems. But increasingly we work with much simpler systems, which are essentially tubes. So these are capillaries or fine plastic tubes through which we flow our reagents. So you can see in this very simple example here, we have a syringe loaded with a reagent, we depress the syringe, and the reagents are forced through the tube, and within the tube we carry out standard chemical processes. But as I say, the advantage of moving to this kind of approach really lies partly in the improved control we can get, and also in the ease of automating chemical processes. So one of our goals in my group is to develop chemical systems that are completely self-contained. So they'll carry out every single step of a chemical synthesis in a single inline process. And I wouldn't say we're there yet, but we've certainly been developing many of the tools required to achieve that goal. So to give you an early example of some of the work we did in this field, we started off by trying to synthesize quantum dots. And here, the spectral characteristics of the quantum dots are intimately related to the size and the shape of the nanocrystals you're making. And in particular, the emission characteristics, the band edge emission peak you can see here, this sharp Gaussian peak, its wavelength is dependent on the size of the quantum dot. So the larger the crystal, the weaker the quantum confinement, and the longer the wavelength of the emission. So by tuning the size of the nanocrystal, you can essentially shift this emission wavelength from the blue side of the spectrum all the way through to the red side of the spectrum. You can see that here. This is just data based on microscopy of quantum dots, of cadmium selenide quantum dots of various sizes, just plotting the peak wavelength versus the radius, and you can see that there's a smooth progressive change in the peak wavelength as we change the nanocrystal size. So this is a very nice system for evaluating flow chemistry, because we can make quantum dots in our flow reactors and we can analyze them spectroscopically, and from that we can tell how much control we have over the reactions we're carrying out. And so, as I say, we normally work with very simple chemical systems. So pretty much everything I'm going to describe today involves mixing 2 or 3 reagents together and perhaps simply heating them. And this is no exception. Here we have one syringe that's loaded with a cadmium precursor, cadmium oxide, and a second syringe that's loaded with a selenium precursor. And we inject them into the chip. You can see here this was carried out in a simple glass-based chip. One reagent comes in here, the other reagent comes in here. They mix at this point here, and then they meander along the channel, and they're extracted along this point here. So it's a very simple system, but even in a system as simple as this one, we have control over the reaction time, the reagent composition, and the reaction temperature. So if we want to control the reaction or the reagent composition, we can change the relative flow rates of our two precursors. So if we pump in the cadmium faster than we pump in the selenium, we'll end up with a cadmium-rich reaction. If we hold that ratio fixed, but we step up the total flow rate, then our reagents are going to pass through our reactor more quickly, and we're going to decrease the reaction time. And obviously, if we sit this glass chip on top of a hot plate, we can control the reaction temperature. So even in a system like this, which is very simple in conception, we have good control over composition, reaction time, and reaction temperature. And that leads directly to good control over the spectral characteristics of the materials. And so here, for example, you can see the effect of changing the reaction time on the peak wavelength. And you can see it's a very, very smooth progression in the spectral characteristics as the reaction time increases. So what's happening here, we're increasing the reaction time, we're forming larger particles. Those particles exhibit less quantum confinement, so we see a progressive redshift in the emission spectrum. But the nice feature of this data is we're able to tune the peak wavelength to within a fraction of a nanometer. And that's something that's very difficult to achieve in a conventional flask-based reaction. And you can do the same thing with temperature. Again, if you increase the temperature, there's a nice smooth progressive increase in the peak wavelength as we're forming progressively larger particles. So using this system, you can tune the emission of the quantum dots over the full visible spectrum. So it's a nice system for creating nanocrystals. So one of the things you can think about doing with a system like this one is integrating some form of analysis into the reactor. And so as soon as you can think about integrating analysis into the reactor, you can think of introducing some kind of intelligence into your reaction system. So the idea here is that we monitor what we make as it comes out of the reactor, and we pass that information to an algorithm that makes decisions about what reaction conditions to try next. So this is kind of inverting the ordinary approach to chemical synthesis, where you step through different reaction conditions until you get something you like. Here our goal is to create a reactor where we specify what we want, and the reactor is left to find the conditions that will yield that outcome. So the way we do that is we take the reactor I just showed you, so that's shown just here, and we introduce some form of spectral analysis at this point here. So we have a laser coming in and just a simple CCD spectrometer, so we can look at the emission characteristics. We take that information and we pass it to a computer, and we allow the computer to make decisions about how it's going to adjust the temperature and how it's going to adjust the flow rates. So in a way, this is the technique that Bjorn warned against in his talk, which is we're trying to do chemical optimization based on experiments. We're doing an experiment, we're seeing what the outcome is, and then we're doing another experiment immediately afterwards, and we keep iterating until we get the outcome we want. But the key to making this work, of course, is being able to conduct a large number of experiments. And this is one of the things that flow chemistry allows you to do. It allows you to trawl through very large numbers of reaction conditions relatively quickly, giving you access to much larger parameter spaces than you would have if you were doing this kind of thing by hand. So just to give you a very simple example of this kind of approach in action, here we just have a single parameter we're trying to adjust, which is the flow rate, and we're trying to adjust the flow rate in order to obtain nanoparticles that emit at this wavelength here, 525 nanometers. So what you'll see in a moment in the top plot is the emission spectrum after each new set of reaction conditions, and in the bottom plot you'll see the flow rate for each of those reactions. So what you'll see is the flow rate jumps about all over the place to begin with, and it gradually converges to a final value. Whereas in the top plot, what you'll see is the spectrum jumping all over the place and gradually converging to a final spectrum. And what's happening is the algorithm is building up a picture of how the product depends on the reaction conditions, and it's gradually adapting the reaction conditions until the target is achieved. So here we see the spectrum jumping around. Here you can see the flow rate jumping around, and gradually you can see a stabilization of the flow rate here, and the shift of the spectrum becomes weaker, and gradually just after 20 or 30 measurements we've reached a final point which is more or less bang on target. So this is a very simple example of where we're simply controlling one parameter, which is the flow rate, to control another parameter, which is the emission wavelength. But typically in chemical synthesis, that's not what you're trying to do. You're trying to use multiple parameters to control multiple other parameters. So in quantum dot synthesis, a very good example of that would be to say, it's not just the peak wavelength I care about, but I also care about the emission intensity. How am I going to maximize that intensity? So if I only have a single parameter to play with, there's only a single flow rate that's going to give rise to the correct emission wavelength, so I have no independent control over the intensity. But as soon as I introduce the ability to simultaneously vary the temperature and the reaction mixture, there'll then be multiple reaction condition combinations that give rise to my target wavelength, but some of those will correspond to nanocrystals that emit very strongly, and other conditions will correspond to nanocrystals that emit very weakly. And what I want to be able to do with the algorithms is identify conditions that will optimize both the intensity, or will optimize the intensity for my target wavelength. And so this all really boils down to the intelligence you build into your algorithm, and you want an algorithm that has certain characteristics in order for this to work. So firstly, as Bjorn was explaining in the morning, you typically want a global optimization routine, so something that in principle can search the entire parameter space. It needs to be multidimensional, so it needs to be efficient at exploring the effect of many parameters at once. And because we're dealing with experiments which typically take anywhere from half a minute to 10 minutes, it has to be a relatively efficient algorithm. So it has to be one that can explore this space very efficiently. And so this, in our case, forces us to use response surface approaches, which try to create a model that simulates the behavior of the system and then determines where to look next on the basis of the features in that model. So for example, if the model says there's an optimum to be found in this location, the algorithm will request the reactor to carry out a reaction at those conditions in the hope that the real experimental system will behave in the same way. So it's constantly carrying out more measurements to improve its model, and hopefully in the process of doing that, it's homing in on the target outcome. And one other thing I should say is these algorithms, because we're dealing with experimental systems, they have to be noise tolerant. So there are always going to be examples of effects that are out of your control. It might be down to vibration in the system, or it might be due to electrical noise. Little things can give rise to outliers, or even just noisy looking data, and you need an algorithm that's capable of tolerating some degree of noise. The less noise you can engineer into the system, the better, but there's always going to be some noise that's left behind that the algorithm has to be able to handle. So finding systems that are capable of doing this is quite a challenge, but it's also a huge area of research in the field of applied mathematics. So we've kind of picked and chosen the best algorithms for our purposes, and some of them have turned out to work rather well. So this is a rather messy plot, but what you can see here is the algorithm trying to test out different reaction conditions. So it's varying the three parameters at once. It's varying the flow rate of cadmium oxide, the flow rate of selenium, and the temperature. And Each of the dots corresponds to a different set of reaction conditions, and the colour of those dots tells me how happy I am with the outcome. And the way we set up our problems, the lower the value we measure, the happier we are. So in exactly the way that Bjorn was explaining this morning, we create a fitness function that specifies how close our current product is to what we want. And we define our fitness function so that lower fitness values correspond to a better product. So what our optimization routine is trying to do, it's trying to minimize the value of that fitness parameter. And so you can see a cluster of blue points here. So the color bar has somehow left this diagram, but blue is lower. So you can see there's a cluster of points here of low values. But you can also see that there are some lower values down here. So that immediately tells you that we're dealing with a system with multiple optima. And that kind of indicates why it's so important to look at a global optimization routine. The lowest values are found in this cluster here, but a local optimizer might well get trapped over here where the values are small, but not the very smallest they could be. So if we look at the spectra that corresponds to the best points so far. So we've done a certain number of measurements, and within that set of measurements, one point corresponds to the lowest fitness value. What we've done is we've plotted that lowest value here all the way through our search, and you can see obviously when we start, the lowest value is the first data point we measure. It so happens that the second one was an improvement on the first point. We then didn't get an improvement until the 6th point, and then until the 19th point. And what you can see here, not very clearly I must admit, is what you can see is that as we go further and further through the search, we're homing in on our target wavelength, but we're also increasing the intensity of the emission. And you can see that at the optimum, this is the optimum point here, we've exactly focused in on our target wavelength. So the algorithm has achieved what we wanted it to do. So there's an example of applying chemical optimization to optimizing materials properties. So here we're trying to balance intensity and a target wavelength. We can also apply the same approach to optimizing the yield of a chemical reaction. So here, this is work that we've done quite recently, where we've been trying to make xylenyl functionalized C60. So I'll do what John Anthony warned against. As not being a synthetic chemist, I'm now going to try and struggle through a synthesis mechanism. But I'm going to jump to the point here. So what we're trying to do is we're trying to functionalize C60 with xylenyl adducts. And so depending on how far we allow our reaction to progress, we either form a singly functionalized C60, a doubly functionalized C60, or a triply functionalized C60. And so this is a kind of I would call this a cascade reaction. So we start at x0 with no functionalization, and we progress through to x3, and if we allow the reaction to continue further, we might even form higher adducts. You can certainly form x4. We've seen that in some of our reactions. But the point about this kind of reaction is, except at the starting point where you have 100% C60, if you freeze this reaction at any point, you will have a mixture of products. So if you use relatively short reaction times, you can expect x0 and x1 here, the lower order derivatives, to dominate the product mix. If you move to longer reaction times, for example, you can expect x2 and x3 to dominate the product mix. But because we're moving through a range of intermediates, if we freeze the reaction at any point, there will be more than one product. So this is the case where you can't, unfortunately, you can't select a single, you can't guarantee a yield of 100% because there's no endpoint to this reaction. In principle, this reaction carries on to higher and higher order adducts until everything is sterically hindered and the reaction can't proceed further, or you've depleted your saltine here and you've reached the end of the reaction. But what we really want to do in practice in the field of electronics, it turns out that these two middle adducts, X1 and X2 are the ones that we want to target. X0 is C60, so that's not very soluble, and X3 has rather poor electronic properties. So in practice, what you find people wanting to do, they either want to maximize the amount of X1 or the amount of X2. And so it's interesting to ask, can we use the flow system to optimize our reaction mixture? And so we've tried to do that using a very similar setup to the one I just described. In this case, we have saltine, which is this reagent here. In one of our syringes, we have C60 in the other one. We pass them into a heated coil, and then this time we analyze by HPLC. So HPLC is a nice technique for analyzing the composition of complex mixtures. So here we choose a column that's been functionalized to be selective towards, or to have a strong affinity towards C60. So this is the system we use. I think that's probably... And so before we try any optimization, we can just try it out and see if it actually works as a means of synthesizing our adducts. And here we're looking at the effect of temperature. And I've labeled the different peaks. This is X0, so this is unreacted C60, which comes out last. Here we have X1, the singly functionalized derivative. X2 is the doubly functionalized derivative, and the triply functionalized derivative. And what you can see, as you might expect, as the temperature increases from low temperature here up to high temperature here, the amount of C60 is decreasing because we're taking the reaction to, we're progressing the reaction further, so we're depleting C60, and we're creating more of our other adducts. And the same thing happens, and so what we can do is we can take this data and we can calculate the mole fraction of each of our different derivatives, and we can plot that out as a function of temperature, and that's what you can see here. So the blue zone here tells me the amount of C60, I would say brown, but I'm colorblind. This region here tells me the amount of the singly functionalized derivative, and the yellow zone here tells me the amount of the doubly functionalized derivative, and there's barely any in this plot of the triply functionalized derivative. But what you can see, as I just explained to you there, the amount of C60 is falling away, and the amount of the first and second order derivatives is increasing. So we're gaining first and second order derivatives at the expense of our reagent, which is not surprising. And we can do a similar thing, mapping out, just varying the time or varying out the ratio of saltine to C60. And it turns out that for the conditions I've looked at here, increasing the temperature, increasing the time, or increasing the amount of saltine has more or less the same effect. It creates more of the higher order derivatives at the expense of C60. But of course, in each of these cases, I'm only varying one parameter at once. So this is 6 measurements. This is another 6 measurements, and this is another 6 measurements. So it's given me a very limited view of how the product depends on the reaction conditions. And that should be fairly obvious because in all of these plots, the amount of the first order derivative is increasing from left to right. But I know that if I allow my reaction to continue further, then I'm going to start depleting my first order derivative in order to make higher order derivatives. So you can see that this is an incomplete picture. So what we can think about doing is exactly the same thing, but mapping out or varying all 3 reaction parameters at once. And here we've done this at a relatively crude level. So this is 6 temperatures, 6 reaction times, and 6 reagent compositions. And each of the data points here is a different measurement. And hopefully, you don't have to look at this too carefully, but hopefully if you look from top to bottom or from left to right, you can see that this system is behaving in a nice, smooth fashion. So you can see that without even studying what's happening on a detailed level, the reactor is giving us good control over the product. And so this is one way that you can find the product you want. You can just look through what we've done here and find the best match to your requirements. But there are 2 drawbacks to doing that. Firstly, this is 6 times 6 times 6, 216, I might have got that wrong. It's 6 cubed measurements, right? So it's quite a lot of measurements to do in order to find what you want. But the second thing is, we've only allowed our temperature to take 6 values. We've only allowed our composition to take 6 values. We've only allowed our reaction time to take 6 values. So it's a very discrete, very sparse mapping out of the parameter space. What you would like to do is not do 6 by 6 by 6, but maybe 100 by 100 by 100. So that would be 1,000,000 measurements. And suddenly you're no longer in the world of reality. So this is the point at which Bjorn's earlier point absolutely holds true, which is if you try to push this kind of approach too far, you just run out of time. And when you run out of material, you can't do the number of measurements you want to get a good quality optimization. So here, this is where you rely on the algorithms that I was talking about earlier. If you can choose an algorithm that essentially sniffs out the optima and focuses its attention primarily in where it knows good results are likely to be found, you can find the optima much more efficiently, and you can do that at a higher resolution than this kind of linear searching will give you. And so that's what we've tried to do here. We've taken the reaction system I showed you earlier, and we do exactly the same thing. So we take our chromatogram, we extract our mole fractions, and we pass those mole fractions to our algorithm that then decides how it wants to update the flow rates and the temperatures. And what we've tried to do here, and this is, I think we're only at the early stages of being able to do this well, but what we've tried to do is develop rules that will allow us to define what we want in words and then translate them into a mathematical function that the optimizer can deal with. And so this is just an example of the kind of thing we've tried to do. So what we've tried to do is we've tried to maximize the yield, or ensure a minimum yield, I should say, of these two middle order derivatives. So this is the singly and doubly functionalized materials. So if I wanted to ensure that I got nothing but x1, one way of doing that would be to have a very short reaction time. And then only a small amount of my C60 would become functionalized, so I'd end up with a mixture of unreacted reagent and my singly functionalized derivative, and nothing else. So I could get a lot of x1. If I wanted a lot of x2, I can let my reaction go a long, long way, but what's going to happen then is in making a lot of x2, I'm going to start making some x3, which I don't want. So what we've tried to do here is we've said, these are the two derivatives that are of most interest electronically. Let's ensure that collectively they provide a yield of 90%. And then we looked at two extreme examples. One is, let's maximize the ratio x1 over x2. So let's try to ensure that we have a solution that's rich in the first order derivative. And as an alternative challenge, let's minimize that ratio. So let's try to create a product that's rich in the second order derivative. So we take those wordy requirements and we re-implement them within our algorithms, and this is what pops out. So if we try to maximize the ratio of x1 over x2, you can see that we can get essentially a 4-fold excess of x1 relative to x2. As I said to you before, by the very nature of the reaction, we can't pick out a single reaction product. The only way we'd be able to do that is by changing the chemistry in some way, so that we inhibited additional functionalization of the target. So here we're able to get a 4-fold excess of x1 relative to x2, and you can see if you look at this plot here, this is x0, this is x1, this is x2. We're left behind with essentially 10% thereabouts of unreacted material. So we're at the early stages of the reaction in order to achieve this outcome. On the other hand, here we haven't done quite so well. We've still got an excess of x1 over x2, and that's something that you can't get around. We're limited by the kinetics of the reaction, but we've certainly tilted the balance. So now we have approximately, I don't know what this is just over a third x2. But we've achieved that now by producing a small amount of the third order derivative. So we're still restricted by the kinetics of the reaction, but we've squeezed the optimum we can out of the system just by allowing the algorithm to satisfy the criteria explained above. What time is it?
4.
I should stop, yeah? No. I could continue for hours, so I think I will. I'll stop there. But what we're trying to do now is we're trying to develop a range of tools that we can apply to alternative. In fact, James is going to cover some of these things. So we also carry out these reactions in a slightly different way. So in a two-phase system where we create droplets, and this gives, as James will show you, this gives us access to acquiring data much more quickly than anything I've described here. And we're hoping that by developing a mixture of techniques for carrying out chemistry very quickly, techniques for analysing the products very quickly, and algorithms that can handle a huge amount of data, we're hoping that we'll be able to massively increase the amount of, or our ability to search very large parameter spaces. And our hope ultimately is we'll begin to be able to discover new material systems or new unexplored reaction conditions that a conventional chemist would not think about looking at because they're so far out of normal experience that they're considered not worth exploring. If you develop tools that can explore spaces extremely quickly, then you have the potential to do, hopefully, new chemistry and discover new materials that just aren't accessible by conventional techniques. So that's where we're hoping this kind of approach will lead, but that's many years off, I suspect, but that's what we're trying to do in my group. So apologies for overrunning. Thank you.
Thank you, John, for a very interesting talk. Questions?
Okay, I can try to speak loudly. Can you hear me? Yeah?
I can hear.
Yeah. Okay. I think this is very interesting work. I was thinking that using HPLC to separate out and look at the different components, and this is something that can be expanded and made also more efficient, maybe using chemometrics, because in chemometrics you are trying to create artificial selectivity through maybe using spectroscopy or something like that. So in this case, what you could have done maybe, this is just a suggestion, and that is to make a model, let's say going from near-infrared spectroscopy and the concentration of the different fullerene components, and then after doing that, then you can just pass it through a near-infrared spectrometer, and it will increase the speed quite a lot. That's one thing, but the other thing is, let's say you wanted to search for a certain property that is not so easy to have a sensor for. It could be something a little bit more diffuse. Again, you could use maybe the same approach and then still have your system, which is just brilliant, and then it would be expanding even more maybe.
Yeah, no, absolutely. I think in this particular case I showed you here, the limiting factor is less the analysis, it's 50-50 the analysis and the carrying out the reactions. The reactions are relatively slow, the analysis is relatively slow, so it may be, at worst it trebles the total time. But we're also looking at droplet-based systems where we can generate different compositions very, very quickly. And here HPLC would be a complete waste of time. So what we definitely have to use there are spectroscopic techniques that can give us instant information. And as you say, I think our current focus is going to be in sort of mid-infrared spectroscopy, but you've kind of told me a little bit about this before, but I think absolutely a near-infrared spectroscopy would be a hugely fruitful approach as well. So yeah, I'm keen to talk further about that.
Okay. There it does.
Cheers, John. Really interesting. I hadn't seen this work before. Have you looked into what the pharmaceutical chemists call DOE, or design of experiments?
Yes.
It's because I mean I saw a lecture by them, and it was that they give you sort of counterintuitive suggestions, but it lets you sort of do grid kind of stuff like this. That apparently is really amazing. I don't know if there's that sort of.
So there's a slight distinction between optimization and design of experiments. So in design of experiments, typically, I'm sure there are plenty of variations, but typically you decide up front what conditions you're going to test, and you try to. Allowing for a certain amount of randomization, you try to fill the parameter space. So a typical way to do that would be you say, I'm going to test 10 different temperatures and 10 different compositions, and you have one data point for each temperature and one data point for each composition. So you only have 10 data points in total, but you've in some sense tested out a parameter space of 100. You've sampled it sparsely. We sometimes do that right at the outset to build up the very initial picture. That's often something we'll do within our algorithms, but the distinction is thereafter. So the importance of optimization is you look at what you've measured so far, and then you make new decisions based on what you've discovered. So you very quickly, hopefully, you find out where the unpromising areas are and where the promising areas are, and the algorithm refocuses its attention to the promising areas. So I think there are limits to what you can achieve with a DOE approach. It's good for an initial exploration, but beyond that initial exploration, you then want to, in my view, you want to switch to optimization.
I love this stuff, and this is also the first time I've seen this big as well. Really practical question, and in the back of my mind I've got an answer, but I want to hear your explanation. Doing one of these reactions, heating the solvent well above its boiling point in a reaction that also generates a gas.
Very good question. So within that reactor is something that's rather crucial to making this work, which is the back pressure regulator. So we work at, James, you'll probably remember 5 bar, is it? We typically work at 5 bar in order to prevent those two processes. And it works quite well. I mean,
under pressure.
Yeah. But it's low tech. I mean, it's literally a spring, a spring-loaded valve. So implementation is very straightforward. It really adds no complexity, and not so much in the case I've shown here, but for some of the things James will show, that back pressure regulator also improves the flow characteristics immeasurably. So I think we invariably use back pressure regulators these days. Would that be fair to say?
Yeah, in a continuous flow system. In droplets it's a bit more difficult.
And what is actually your flow regime? Is it turbulent or laminar?
Laminar. So our channel dimensions, I mean, we push the extremes of what you can get away with, but we're a little bit less than 1 millimeter diameter in our channels. If we work in chips, then we're working at a few hundred microns.
You're using a syringe pump, right?
We use syringe pumps, yeah.
Have you seen any effective oscillations? Because we have that problem in our system.
Yeah, we spend lots and lots of time balancing things to get nice stable flow. So if you don't balance things well, you don't use the right back pressure regulators, then you can experience problems. We kind of play around until we've got nice stable flow.
Yes, I'm just wondering, have you tried to think about this in terms of fluid chemistry? Is it possible to see this be expanded into that area where you can test out and synthesize like large number of different...
Yeah, no, absolutely. And so this is something that I was talking to one of my PhD students about only the other day. For me, one of the interesting areas will be to look at how we can combine very fast measurements. So for example, you can update reaction compositions quite quickly just by adjusting flow rates with things that are harder to change, like the temperature. If you change the temperature, you have to wait for the system to stabilize. It's got a certain thermal mass. You can't update the temperature more than a few times, once every few minutes. So I'm kind of interested in techniques that will allow us to change some things very quickly and other things slower. And so that will be a kind of an incorporation of combinatorial approaches into what I've described here. But we haven't done it yet, but it's something that we're hoping to do.
Any more questions? Okay, John, thank you very much.
Thank you.